In previous video, we have studied the half-wave rectifier using diode. In this experiment, we are going to learn the full-wave bridge rectifier. So this is the circuit diagram for full-wave bridge rectifier. Here, instead of transformer, I have used AC voltage source here. You can write transformer also. It consists of 4 diodes, and the diodes are connected in the form of a bridge, with only 2 diodes conducting current during each half cycle, and the 2 diodes D1 and D2 during positive half cycle of the input supply, and D4 and D3 during the negative half cycle. And so in this way, 2 diodes will conduct during each half cycle. And how to connect the diodes? The D1 and D2 should be connected in opposite arms, and they should face downwards, anode upper side and cathode downward direction. And D3 and D4, they should be connected in other 2 opposite arms, and they should be facing in upper direction, cathode and cathode of both the diodes in upper direction, and anode. And anode of this diode, both should be shorted, and cathode of D1 and cathode of D3 should be shorted, and the load resistor is connected between the 2 points, cathode connection and anode connection. And between anode and cathode, the voltage source is connected. One end of voltage source is connected, and at the point joining the cathode and anode of the 2 diodes, and the negative other end of the voltage source is connected to the cathode and anode of the other 2 diodes. So in this way, we are going to do the connection in Proteus. And during positive half cycle, what happens, we will check. During positive half cycle, this end becomes positive and this end becomes negative. When this is positive, when positive is applied to anode, the diode D1 is forward biased. And when positive is applied to cathode of this diode becomes reverse biased. In the same way, when negative is applied to D2, the diode D2 is forward biased. When negative is applied to anode of this diode, so the diode D3 is reverse biased. So during positive half cycle, only diode D1 and D2 are forward biased, and diode D3 and D4 are reverse biased. When both D1 and D2 are forward biased, they start conducting because they act as a closed switch. Current starts flowing from the voltage source, positive terminal of the voltage source. See the direction of the current through the diode D1. See the direction through the load resistor. See the direction through the diode D2 and back to the negative terminal of the supply. So it should be a closed circuit. If current starts from positive terminal of the supply and it should end at negative terminal of the supply, then only you have done the connection correctly. It understood. So this happens during the positive half cycle. So how the current is flowing? The current is flowing in this direction. Remember, during negative half cycle also, we should check the direction of the current. Now, during positive half cycle, the direction of the current is in this direction, upper to the lower side. Okay. Then during negative half cycle, what happens? During negative half cycle, this end becomes negative and this end becomes positive. When negative is applied to D1, this is reverse biased. When negative is applied to D4, this is forward biased. And when positive is applied to D3, D3 is forward biased. When positive is applied to D2, D2 is reverse biased. So during negative half cycle, D1 and D2 are reverse biased. D3 and D4 are forward biased. So when these two are forward biased, they act as a closed switch. When these two are reverse biased, they act as a open switch. We all know that in open switch, current won't flow. Then how the current starts flowing? The current starts flowing from the positive supply, and see the direction of the current, green, through the diode D3 through the load resistor and see the direction through the diode D4 and back to negative terminal of the supply. So in this in negative half cycle also the current is flowing in a downward direction, and see the upper cycle in positive half cycle also the current is flowing in the downward direction. So during both the half cycle the current is flowing in the same direction, so that we call it as the current is unidirectional. So when current is unidirectional, the voltage developed across the load is unidirectional. When current is unidirectional, the voltage is also unidirectional. So in this way, we get the output voltage across the load register, and that voltage we refer it as a DC voltage, because when the voltage is in unidirectional, the unidirectional voltage is nothing but a DC voltage. So VDC is equal to the formula is 2 Vm by pi. So the formula is 2 Vm by pi for the full wave bridge rectifier. VDC is equal to 2 Vm by pi. So 2 by pi, if you calculate in a calculator, it becomes 0.637 Vmax. So what is Vmax? It is root 2 Vrms. Vmax is nothing but root 2 Vrms. If you multiply 0.637 into root 2, I'll get 0.9 Vrms. So the VDC in full wave bridge rectifier is 0.637 Vmax or 0.9 Vrms. So you should remember this formula for the full wave rectifier, and the output waveform, it looks like this. So during positive half cycle, the current is flowing in the same direction. During negative half cycle also, current is flowing in the same direction. So we get during positive half cycle also output, during negative half cycle also output, positive half cycle, negative half cycle. In all half cycles, we are getting output in the positive direction. So this is about the output waveform of full wave bridge rectifier, and this output we call it as a pulsating DC, because we know that DC means we should get a straight line, but it is in the form of pulses. So we refer the output voltage of the full wave bridge rectifier is a pulsating DC. Now I will show you how to construct this circuit using a Proteus. So now let us click the, and now we will open the Proteus software, and I'll show you how to construct this circuit. Now click on new project. Click on give the name of the project as full wave rectifier. Full wave rectifier. Click on next, 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 finish. Okay. So here, click on component mode. Search for V sign. Here I am not using transformer, step down transformer. I am using AC voltage source. V sign you click on this and click OK and place somewhere here. Okay. Now right click on this, go to edit properties, write the amplitude as 230 volts and frequency as 50 Hertz and click OK. Now, see the right side of the screen. I need 4 diodes, D1, D2, D3 and D4. So search for diode 1N4007. So take the second one, silicon rectifier. Click OK. So I'll tell you how to connect this circuit very easily. So D1 I'll place here. This is my D1. And D1 I'll place here. D2 I'll place this side. See, this is D1, this is D2. Both are in opposite arms. And I'll place D3 here. This is my D3. And in exactly opposite, I'll place D4. See, D1, D2, D3, D4. D1, D2, D3, D4. Now how to do the connection? D2, D4 anode must be connected to each other. D2 and D4 connect the anode over, and D1 cathode and D3 cathode. D1 cathode and D3 cathode. Correct? Next, I'll remove this wire. I'll do it neatly. Delete wire. So I'll take one wire. Okay. Next, cathode of D4 and anode of D1. Cathode of D4 and anode of D1 over, and similarly cathode of D2 and anode of D1. Okay. So very simple connection. Two diodes in series and two diodes in series. And where the AC source must be connected? Cathode anode here. So connect the cathode anode to the AC source. Other terminal of the AC source must be connected to cathode and diode of D3. This side. Go here, take one wire and do the connection. Over. Okay. Next, where the load must be connected? Between cathode and anode. See the diode resistor connection. One end is gone to cathode, other end has gone to anode. So this is anode. This is cathode. I'll search one resistor. Okay. So take one resistor. Generic resistor. Click OK and place somewhere in the middle and do the connection between this and this. So now you check, it is looking exactly on the right side of the screen. Now I want to set the value to 1 kilo ohm. Right click on this. So make it as 1 kilo ohm. Click OK. Now connection is over. Now I want to see the result in a CRO. So click here, get CRO and place here CRO. So A channel I'll make for input to check the input. Input waveform is sinusoidal waveform. And output waveform is blue one. I'll connect across the register. Okay. So everything is over now. Now I'll simulate. See the symbol here. This is run simulation symbol. I'll click on this. Now the CRO display is coming here. I'll place it on the right side. Okay. So before right side, I'll show you the waveform. I'll show the waveform. This is my waveform. And see the CRO waveform. So you need to adjust some CRO settings. So we are not using channel C and channel D. I'll turn off channel C and I'll turn off channel D. Now, what you should do, you should make channel A and channel B both in a ground position before. Keep this in ground and channel B also in a ground. Now, you have to overlap the two lines, one over the other. Okay. Now, according to the connection, yellow is input and blue is output. You see here. So yellow is input. So input is AC. Keep this in AC. And blue is output. Output is in DC. And you reduce the amplitude. And this also you reduce the amplitude. And frequency you vary, time period. Now you can check here. See here. So during negative half cycle also I am getting output. During positive half cycle output, during negative half cycle also output. So during positive half cycle blue is output. During negative half cycle also I am getting the output in same direction. During positive half cycle positive output, during negative cycle also positive output. So I am getting the same output as I have shown in the right side of the screen. So this is a pulsating DC. In this way, you can construct the Proteus circuit, full wave bridge rectifier using Proteus circuit. So in next video, I'll show you on how to make this pulsating DC as a smooth DC. So we should use the filter circuit at the output of the bridge rectifier in order to remove these pulses. If I remove the pulses, my DC becomes a pure DC. So in order to get pure DC, I should use a filter. Filter here, we can use the capacitor filter to remove the DC, pulsating DC. That I'll show you in the next video.